All right, guys. Next thing we're going to talk about is the vector product, and we're going to give it a deeper detail, even though we kind of covered it a bit in class. Um, okay, so but before we do that, we're going to review. Okay, so here's our vector product. We're going to review scalar product. All right. Okay, we're going to review our scalar product. And the last time we saw scalar product, or one of the last times we did it, was work was equal to our force times our displacement. And another way of, and so we found that the magnitude for this would just be force times the, I'm sorry, the vector shouldn't be there. Force times r times cosine of the angle between them, or cosine theta. Another way of thinking about this is that it is just the product. It's the product of the amount that this one is in the direction of the radius. That the force is in the or it could be the other way. The product of how much of the radius is in the direction of the force. That doesn't really matter. But it's sort of it's this projection. So if you have force and you have this radius, then it is the perpendicular projection. So it's this component of, so you have r, so this is r, right? And then this little distance right here is f cosine theta, if that's our theta. And I know I totally flubbed that up, but you see that this component is the cosine component of our force, so that's what's the direction as the r, and so it's the amount of the direction into r, and so that's our dot product. It is designed to give us a scalar quantity. It's designed to give us just a value without worrying too much about the direction. Now, torque changed things. Okay, torque. Okay, we gave us a magnitude now of RF sine theta, and we're going to explore that a little bit. So we're going to create a circle here. All right, so again, we're going to do it in perspective. So there's a disk, and we have an axis through the center of the disk. All right, and we're going to have a radius. You guys may notice that I'm doing radius in red right now. Okay, we have radius out to the edge of the circle. Okay, and then we have a force, and our force might not be in the direction of the circle. Our force might be off at an angle in that direction. Here's our force, okay, which is sort of in an off direction. This usually shows up better. There we go, if it's out of the light a little bit. All right, so that's the direction of our force. Now, our radius continues on in this direction. So that's the direction of the radius vector. And there would be a angle here in between them, and that's going to be our theta. Now, one way to think about this is the more perpendicular, okay, so if we get our force to actually go more perpendicular to the direction of our radius, the greater our torque is going to be. And so if we create this, if we make our force go from here rather than, we put it in perpendicular to our radius, then all of a sudden we're going to increase the amount of torque, because we don't have any we don't have any air quote wasted force that is, that's not in the perpendicular direction to our radius. Okay, so think about it like this: what happens if our force is parallel to our radius? What happens if we actually pull? Okay, if the force is in this direction to the direction of the radius. So here's our radius, and we actually do this to it. Is this going to cause any spin on the disk? I take it back. No, that's right. If the force is parallel to the radius, if they're in the same direction. So if we do this to the force, does that cause the disk to spin? And it should be no. And that's, so if you look at the RF sine theta, if theta equals 180, or if theta equals 0, because they're in the same direction, then sine of 0 is 0, and so there's not going to be any torque if it's in the same direction. Okay, so the purpose of our vector product, which is what we're getting to, is if we're trying to multiply a vector by a vector to get another vector. So we'll multiply two vectors together, and we want to have a vector coming out of this. Here's what happens. We get, and the way we do this is according to the right-hand rule, and we've talked about this a bit. The order is in, it is in this order, and so the actual formula for torque equals R cross F, and we use this as a new operator which defines the torque vector as the radius in a cross product with the force vector. Now, this is still R times F, and so if you know that they are perpendicular to each other, then they're going to be, then it's just straight up multiplication. But if, and so that's why we call this cross product. Now we come back up here, and this is, we don't usually refer to this as the scalar product, although your esoteric professors when you go to college may call them the scalar product just because they want to sound smarter than you. We call it dot product. Because it's easier to say than scalar product, and it is more descriptive of the operator that we're using there. That is the scalar product of the two. We call it the dot product because we write it with a dot. Okay, and well, what this does here is that this is going to give us two values here. Our torque is going to give us, our torque vector is going to equal the magnitude of R times F times sine of theta. Okay, that's the magnitude. Times the right-hand rule, and the direction is going to be according to the right-hand rule. And here's the right-hand rule, that if you have two vectors, okay, and so in this case we have R, and you put the two vectors tail to tail, and you move one. So I'm going to have to rotate my paper here to illustrate what I'm talking about here. So here's my radius, and I'm going to turn my fingers into the direction of the other, where the other vector is, and that gives me up into the camera as my direction. Well, on this paper here, this winds up being, instead of being up into the camera, the way we've drawn it is our torque is actually in the up direction here, and this becomes tau is up there, and that's kind of messy. All right, so that's our tau, and that is the result of R cross F, and we find that direction as a result of the right-hand rule. Okay, so we're going to get a little bit, and what this actually defines is it is a normal vector, and so if you think about a normal force and how we define that as being perpendicular to the that's perpendicular to the surface of contact between two objects. A normal, the math term for normal is actually how is how a plane is defined is by its normal vector. And so if you can have, it's kind of similar to if you find the tangent plane to a surface at any particular point, the normal vector defines what that plane is. So that's why we have this torque coming out, and that defines the plane of these two vectors being that are crossed into each other. So we're gonna do some math and some actual just pure math here for our vector operation. We're going to define a vector C. Our vector C is defined as vector A crossed with a vector B. This is going to equal AB sine theta. The book uses phi. I don't, because that's phi, and I often use that to be my zero, and I am not precise enough with my handwriting to distinguish between those, and so I won't expect you guys to do that. So I just use theta, and hopefully, and I trust you guys to be able to recognize that it's the angle between them. AB sine theta, and then we have the right-hand rule. So this is the magnitude. And then we use the right-hand rule, which forevermore in this class we'll refer to the right-hand rule as RHR to determine where the vector is. Now we've been through this before. We talked about it matters now. The order of the vectors matters now, because it changes the direction of the vector if we don't use, if we aren't paying attention to which order it goes in, because it is always, your fingers start in the direction of vector A and it curls into vector B. So let's draw this here. We have vector A. Here's A, and here is B, and that is theta. And so A cross B is now, everything we've had is into the camera. Well, this time it's not, because here's A this time, and we're going to cross it into B, which means my thumb has to go down into the table rather than up into the camera. So the vector of this one is actually going to be, and here's the new thing for you guys maybe, it's going to be a circle with an X in it is going to be the direction of the vector, which means it is into the table and it is out of the plane. It is below the plane, away from you, out of the paper. I think we mentioned this in class one time, but we have two different versions of this, and it's as if you're looking at an arrow. So imagine we draw an arrow. But it's a three-dimensional arrow that has this point to it. And then at the end of the shaft it has tail feathers. Okay, and as we move this arrow around, I wish I could draw in three dimensions, as we move this arrow around and it points at you, you get to see the tip. And so if the arrow is pointing at you, let's darken that tip here. So if you get to point at you, then all you get to see is the tip of the arrow. And that means at you. Okay. Then if you're looking at the back end of the arrow, you see the tail feathers. And that becomes a vector pointed away from you. All right, so in this case, our A crossed with our B is going to result in a vector that is pointing away from you. Okay, and into the paper. All right. Now, that's the case, then what if we did B cross A? Well, B cross A is going to equal B times A sine theta, so the magnitude stays the same. However, we're going to use the right-hand rule again, but that's going to lead to something in the negative C direction. Okay, and so if we reverse the order of two vectors, okay, where we would have C, if C is defined as A cross B, then B cross A is going to equal negative C, and this is how we define, you know, our two cross products. Now, okay, we have some cross product vector rules, and this is going to get kind of this gets mathy. So deal with me here. Let me reset my stuff and zoom in. All right. Yeah, let my camera do its thing because it takes forever for it to refocus. All right. So here are some rules. We know that A dot B equals B dot A, and this equals A B cosine theta, and there's no direction to it. However, A cross B equals negative B cross A. Okay, and here is, and this is where we start changing. This is why the order matters. The distributive property still does work, so we have the distributive property such that A cross vector B plus vector C will equal, that's going to equal A cross B plus A cross C. That still works there, so that's good. However, the product rule, which we're going to use, the product rule is a little different. If we take the time derivative d dt of A cross B, it's a little different, and because normally it would be derivative of A times B and derivative B times A. Well, we have to do it in the particular order because there remains some cross products in there. It equals dA dt cross B plus A cross dB dt. Okay, so it's just like the product rule, except you have to do the first and the first. So it's the derivative of the first times the second, and then the first times the derivative of the second. It's like you're distributing, you have to specifically distribute your operator to both of your vectors, and the order does matter. First comes first, second, second. Now, this next part we've talked a little bit about, that I dot I cross I is going to equal, well, it equals 1 times sine of 0. Well, sine of 0 is 0, so that becomes 0. All right, J cross J and K cross K also both equal 0, just following the same rules there. However, when we start crossing other things, it gets there are certain rules we have to follow. So here's how I've memorized it. And you draw the back corner of a box. So here's Y, here's X, and here is Z. I'm sorry, no, that's not Y. That is X. And this is Y. All right, so Y continues down, and X continues over, and Z goes back. And so if we have, and this is I hat, and j hat and k hat. And so then the way these work is I cross j equals k. And conversely, j cross I is going to equal negative k. All right, so the order is switched, and so forth becomes negative. J cross k equals I hat, and k cross j equals negative I hat. And then k cross I equals j hat, and I cross k, I'll make sure I'm getting these in the right order, is going to equal negative j hat. So these are the definitions of these values. But then, so if we're going to cross two vectors, we have vector A, which exists as A. Okay, we're going to do A cross B here. So A, if vector A equals AX I hat plus AY j hat plus AZ k hat, and B equals BX I hat plus BY j hat plus BZ k hat, and we're going to cross these. Well, you can see where this becomes a pain in the butt, and this actually becomes a distributive, where these get distributed to each other. But this is actually what matrix and determinants were used for. And there's an example in your book, I think it's 11.8 in your book, that formula 11.8 in your book that will go through the determinants of this and how it works and all that sort of thing. But I'm going to give you what the final answer actually is, because I don't feel like writing it, showing all the determinants and writing it down. But so you'll just have to take my word for it that A cross B equals AYBZ minus AZBY I hat. Notice that these are the y and z components, so it's I cross I is 0, right? And so then it's all right, so then we're just looking for the things that are in the I direction. Well, that's going to be J cross K is in the I direction, right? That's J cross K. That's AYBZ is going to be the first part, and then B times A, or I'm sorry, but K cross J, because remember it has to be A times B. So AZ times BY is going to be in the negative direction, because that's K times J gives us negative I, and that gives us our I hat values. You can go through it. It's tedious, and you can write out the whole. You can do all of the distribution, and I hat times I hat, well, it goes to 0, and then J hat times K hat, and K hat times J hat, and all, and determining whether those are positive or negative I, and all that sort of stuff. That's how it works, and we don't have to use determinants for it, but it's a real pain in the rear, and I'm not going to do it, and you will someday, and you will understand then why I didn't want to do it in my physics lecture, because it's just going to take too much time. Then the middle one is a subtraction, and this is part of the nature of the determinant math, and other than that I can't really explain why. This would be AX BZ minus AZ BX times J hat plus, and I don't have room for it. Okay, another reason why it's a pain in the rear. AX BY minus AY BX K hat, and that is your whole vector right there. Now, we use this now. We're using this now for torque, but we are going to be coming up to angular momentum, and we're going to use it a lot in magnetism. So we're just going to stick with that, and that is it for our vector product. And That was 5 minutes faster than I expected. So we'll see you guys next time.